1 floor every 4 days. That's the pace right now on the Red Sea coast of Saudi Arabia. A tower climbing toward something no building in history has ever touched. 1 kilometer, a full 1,000 meters straight up. The Jeddah Tower isn't just the tallest building ever built. It's the first to cross a threshold that engineers spent 30 years arguing was physically impossible. And it nearly died in a hotel room. Not a storm, not an earthquake, not a foundation failure or a concrete crack or a wind load calculation that didn't hold. A phone call, an arrest, and then nothing for 7 years. A $2 billion concrete skeleton frozen at floor 63, exposed to the Red Sea air, while the world moved on. Right now, in April 2026, that skeleton is alive again. It crossed 96 floors last week. By the time you finish watching this, it may have added another. So here's the question. How do you build the first structure in human history to reach 1 kilometer? And how do you restart it after the longest construction pause of any super tall skyscraper ever built? This is how. The ground beneath Jeddah is the first problem. It always was. The site sits on the Red Sea coastal plain. Not granite bedrock, not stable clay. Reef limestone, coral rock, ancient formations riddled with voids and cavities. Layers of weakly consolidated sandstone, pockets of seawater that have been migrating through the rock for thousands of years. You can't anchor a 1,000,000-ton building to Swiss cheese. The engineering team at Thornton Tomasetti knew this before the first machine hit the ground. Their answer: go deeper than any commercial tower foundation in the world. 270 bored reinforced concrete piles, each one drilled by German contractor Bauer through that unpredictable reef limestone, encountering cavities at random depths, filling every void with sand cement grout before the bore could continue. The piles vary from 1.5 to 1.8 meters in diameter. The deepest reach 105 meters below grade. That's deeper than the Eiffel Tower is tall, straight down, before the first structural load transfers to solid ground. But piles alone don't stop a 1 kilometer building from tipping. The load at the base of this structure will exceed 900,000 tons. That's heavier than every aircraft carrier in the United States Navy combined. Distribute that unevenly, and the tower tilts. A tilt measured in millimeters at floor 1 becomes meters of deviation at floor 167. So Thornton Tomasetti connected all 270 piles to a single continuous concrete raft, 5 meters thick, covering 7,500 square meters of ground. The raft pour consumed 18,260 cubic meters of concrete. That's enough to fill 7 Olympic swimming pools, poured in one continuous operation. Because if they stopped, the slab would crack along the cold joint, and a cracked foundation under the world's tallest building is not a punch list item. The coral reef geology had one more problem waiting: saltwater. The Red Sea environment is aggressive. Salt penetrates ordinary concrete, corrodes the steel reinforcement inside, and begins destroying a structure from within. The concrete mix for Jeddah Tower had to achieve low permeability, not just high strength, and even that wasn't enough. Engineers installed a cathodic protection system through the entire reinforcement network, running electrical current through the steel to reverse the corrosion chemistry. The building fights the sea, continuously, electrically, underground. The foundation took 2 years. What came out of the ground in 2015 was a platform capable of supporting something that had never been built. Now the structure had to go up, and here's where the design becomes either brilliant or insane, depending on how you look at it. No columns, no outriggers, no floor beams, no spandrel beams. Every single vertical structural element in this building is a wall. Thornton Tomasetti designed what they call a buttressed core, a triangular concrete tube at the center, with 3 wing walls extending outward from each corner. Those wings connect back to the core through continuous shear walls running the full height of the tower. Every wall carries both gravity and wind load simultaneously. There are no transfers, no redundant structures, no complexity that can fail. The floor plates are 250mm flat concrete slabs. Simple, fast, repeatable. The reason for this radical simplicity: the concrete pump. To build a kilometer-high structure in reinforced concrete, you need to push wet concrete up the inside of the building to to wherever the formwork currently sits. Every extra complexity, every column, every beam connection, every transfer structure adds time to each floor cycle. At 167 floors, a 2-day floor cycle versus a 4-day floor cycle is the difference between a 2028 completion and a 2032 completion. Time is not just money on this project. Time is credibility. The climbing formwork system jumps upward floor by floor, never stopping. The concrete arrives at the base, enters the high-pressure pumpcrete system, and gets pushed vertically. Currently, the pump reaches approximately 370 meters, the height the tower has achieved as of early April 2026. As the tower climbs higher, the engineering challenge of pumping concrete vertically intensifies. The pressure required to move concrete 600 meters, 700 meters, 800 meters up through a pipe fights gravity at every meter. The concrete mix has to stay workable under that pressure without segregating. Too stiff, and it blocks the line. Too fluid, and it loses structural strength. The limit for concrete pumping has never been tested beyond 800 meters in a live project. Jeddah Tower will push it past 1,000. There was a specific decision made early about concrete strength. Engineers determined that anything above 85 megapascals compressive strength could not be reliably pumped to extreme heights. The contractor's own teams raised the concern. So even though higher strength mixes would have allowed thinner walls and saved material, the team capped the specification. The walls are thicker than they theoretically need to be, because a pump blockage at floor 120 is a catastrophe. And thicker walls you can build beat thinner walls that jam the pump. That's the kind of engineering this building runs on. Not the maximum possible, the maximum achievable. Now the wind. At 1,000 meters, the wind does things it doesn't do anywhere else on Earth. The upper spire of this building will move through air that is less dense, more turbulent, and subject to vortex shedding patterns that would cause a conventional rectangular tower to oscillate violently. Vortex shedding happens when wind separates from opposite sides of a building in alternating cycles, creating pressure pulses that push the structure sideways in a rhythm. If that rhythm matches the building's natural frequency, the tower begins to resonate. It amplifies. At extreme heights, that's not discomfort. That's structural failure. Adrian Smith solved this with shape. The 3-petal footprint is not aesthetic. It is aerodynamic. Each wing of the building terminates at a different height, breaking the symmetry that vortex shedding requires. The spiraling taper of each petal interrupts the wind's ability to lock onto the building's geometry. The wind that hits the Jeddah Tower cannot find a clean surface to organize itself against. It separates, fractures, sheds asymmetrically, and loses its energy before it can build into a resonant force. RWDI, the world's leading wind engineering consultants, confirmed this in wind tunnel testing before a single pile was bored. The building also contains a tuned mass damper inside the spire, a massive counterweight tuned to the tower's natural sway frequency, moving in opposition to wind-induced motion. The Burj Khalifa doesn't have one. The Jeddah Tower does, because at a kilometer, you need every tool available. Then came January 2018. The tower stands at floor 63, roughly 1/3 complete. Concrete is curing in the upper levels. Workers number in the thousands. And then the construction simply stops. The 2017 Saudi anti-corruption purge sweeps through the kingdom. More than 200 businessmen, ministers, and princes are detained at the Ritz-Carlton in Riyadh. Among them, Bakr bin Laden, chairman of Saudi bin Laden Group, the main contractor on Jeddah Tower. The construction contract collapses. Workers stop receiving payment. Within weeks, the site empties. 5,200 workers gone. Cranes idle. Formwork abandoned 63 floors above grade. No handover, no controlled shutdown. The building just stops. The tower sat like that for 7 years. 7 years of Red Sea humidity cycling through exposed rebar connections. 7 years of thermal expansion and contraction in uncured joints. 7 years of the coastal salt environment working on every surface left unprotected. When engineers finally re-entered the structure in 2023 and 2024, the first task was a comprehensive structural audit. Every floor, every wall, every connection point. Because you cannot simply resume pouring concrete on top of a structure that has been exposed and dormant for 7 years. without knowing exactly what condition it's in. Exposed rebar corrodes. Concrete that is partially cured can develop microcracking at joints. The structural health monitoring systems installed during construction, the strain gauges embedded throughout the lower levels, gave the re-entry team a baseline. The data showed the structure had performed better than many feared. The lower walls, protected by completed floor slabs above them, had survived the pause in better condition than the upper exposed levels. Remediation work began in late 2023. Problem areas addressed one by one. New contractor lineup assembled. Turner Construction took over project management in March 2025, calling the site one of the most complex construction environments on Earth. Saudi Bin Laden Group returned as primary contractor, a deliberate choice because they already knew the structure they were building into. Construction officially restarted in January 2025. Floor 64. The pace since then is unlike anything this project has seen. One floor every 3 to 4 days. By April 2025, the tower reached floor 66. August 2025, floor 75. December 2025, floor 80. January 2026. Thornton Tomasetti confirms the structural core is performing exactly as predicted in wind tunnel testing. By April 3, 2026, the structure crossed floor 96. The 100 floor mark approaches. 5,200 workers on site. Over 8 million man-hours accumulated since restart without a single lost time incident. The building is running. And here is what changes as it climbs higher. Every floor above the current height represents engineering territory that has never existed before. The logistics alone become almost impossible to picture. 500,000 cubic meters of concrete total will go into this building. 80,000 tons of steel. The supply chains feeding this site run continuously. Aggregate, cement, reinforcing bar, formwork components, all coordinated through Turner Construction's site management system to prevent the one thing that kills floor cycle time: waiting. The 59 elevators this building will eventually operate require shaft construction that runs parallel to the structural core pour. 3 sky lobbies divide the vertical transportation system into zones, eliminating the need for cables that would weigh more than the elevator cars themselves at extreme height. Double-deck elevator cars serve the upper levels, carrying 2 floors of passengers simultaneously. The observation deck, the world's highest, at 638 meters, requires glass panels that can survive wind pressure differentials and temperature swings of 50 degrees Celsius between the desert floor and the upper atmosphere. That glass is already in fabrication. The structural core, right now, is performing exactly as the models predicted. Not approximately, exactly. The strain gauges embedded in the lower walls confirm it. The anemometers being installed near the spire will, for the first time in engineering history, give us real wind speed data at a kilometer above the Earth's surface. Thornton Tomasetti has committed to publishing that data. Every engineer who designs a super tall building for the next 50 years will use it. Here's the thought that reframes everything you just watched. The Jeddah Tower stopped at floor 63, not because the engineering failed. The piles held, the raft held, the walls held, the concrete pump worked, the wind calculations were right. The building itself never had a problem. It stopped because of one arrest in a hotel ballroom in Riyadh. A political event with no engineering content whatsoever brought the most technically ambitious construction project in human history to a complete halt for 7 years. The kilometer wasn't the hard part. The hard part was everything that has nothing to do with engineering, and yet the building survived it. The structure endured 7 years of Red Sea exposure and came back clean enough to build on. The team is now adding a floor every 4 days. The same foundation that Bauer drilled into coral limestone in 2013 is now carrying 96 floors of reinforced concrete without a measurable deviation. The building didn't need saving, it needed time. If that story reached something in you, subscribe to Megabuilt Files. Every week we find the structures the world is building at the absolute edge of what's physically possible, and we explain exactly how they're doing it. The comment section is open. What should we build next?